So, and this is my exam 3 corrections. The first one, it should be D because the pKi actually inhibits the PFK, and so that will activate the F2,6 bisphosphate. Number 3, it should be C because it's the fructose 1,6 bisphosphate rather than the fructose 6 phosphate, and it still needs the ADP to become ATP. Number 4, it should be C because it doesn't bind NAD plus to the active site. That only happens in the complex E3. Everything else is true for E1 though. The next one should be B. I read it too fast. I thought it said complex 2, so the FADH2 is correct for complex 2. For 8, I put it should be D because low ATP indicates that the cell needs to start glycolysis, therefore increasing PFK1 and then increasing F2,6 bisphosphate. Number 10, it should be D because the glucagon is for low blood sugar, which stops glycolysis. Therefore, the pKa phosphorylates and decreases the need for the enzyme. So it'll inhibit, phosphorylate, and then inhibit. B is, I flipped the 2 around. I read it anaerobic instead of aerobic. So lactate is for anaerobic, pyruvate is for aerobic. Number 12, the answer should be acetyl-CoA. It does start the cycle, but it does not act as an allosteric regulator. So NAD plus does activate and therefore acting as an allosteric. Number 13, it should be pyruvate to lactate. Again, I just flipped it around in my head. I thought just switching it around. 15, it should be B because the exchanges from the ATP from the mitochondrial matrix keeps the ATP balance, whereas D, they both involve the inner mitochondrial membrane, not just one or the other. For 17, it should be 4. There's the formula you can see right there, and I was thinking of like the 1/2 with the complexes, so not 2, but 4. For 18, the answer should be D because it's the coupling of this highly negative reaction allows the reaction to go even though it's still thermodynamically unfavorable. And it is able to work together to create a strong reaction. This one should also be D because a high pKa equals a high gluconeogenesis, therefore a lower need for glycolysis. The activation of the FBPase2 is the activation of gluconeogenesis. This answer should be 839 because I just stopped where I coupled the reaction and got the negative 16.7, but I forgot to do the actual finding the equilibrium constant. So there's the formula. You just take and put all those standard numbers in, and then you get 839. Here, for 26, the correct answer should be 39.5 kilojoules per mole. I don't really know what I was doing, but you take -2 electrons, the Faraday's constant, and then our, for the next reaction. For 27, the free energy is used to pump protons across the mitochondrial inner membrane to create a protein gradient for the ATP synthase. Very brief explanation, but that's exactly what the complex 3 is doing in the system. From here, 28 should be 27 ATP. You get 2 from glycolysis, 5 from NHDA and pyruvate to acetyl-CoA, and in the citric acid cycle, you'll get 20. So a total of 27. 29, you get 7.5 from NADH, 1.5 from FADH2, and then 1 from ATP, so 10 ATP. You'll get 11.5 ATP in 31 because you get 1.5 from the ATP shuttle and then 10 from the citric acid cycle. And then from that, you'll get about 19% of those from the substrate level phosphorylation, because 4 from the substrate level and 18 are non-substrate. This next one should be 8 electrons. 35 should be 3 electrons. 2 CO2, 10 proton, 4 ATP. This one I just flipped the protons around, so it should be 4 protons at complex 1, 2 protons at complex 4. This one, I don't remember what the letters are, but it should be for the PFK enzyme, because that is a major regulation point in the glycolysis. And then in the citric acid cycle, it should be citrate synthase, citrate dehydrogenase, and alpha-ketoglutarate dehydrogenase for those enzymes of regulation. And then the succinyl-CoA to the succinate via the succinyl-CoA synthetase. That is the reaction that conserves energy. So those are all my corrections. Thank you so much.